Hello, this is the next video in a playlist that I'm calling Applied Multivariate Analysis. And we're in Chapter 6, part of this playlist, which I'm calling Discriminant Analysis. And let's jump to today's topic, where is finding discriminant function for several groups. So in the first video in Chapter 6, we looked at deriving the discriminant function for between two groups. So let's assume there's k populations and they have the same covariance matrix, sigma, but distinct population means. We take samples from each of the populations, and there's k different populations. Each observation is a vector with p variables in it. Each observation is independent from one another. Now the discriminant function is a linear combination between the p variables, and mathematically we represent it like this: z is equal to a transpose y, and a is the discriminant function, and this discriminant function best separates the groups, where it maximizes the difference between these k transformed group mean vectors. So the z's can be thought of as this: a transpose y, and then it's literally a1 times the first variable, a2 times the second variable, the pth component of a times the pth variable. And as in the two group case, we want the vector a, of course, that maximizes or maximally separates the transformed group means. Now in the two group case, we derived the discriminant function this way. So we wanted to maximize this quantity. And if you back solved, or back substituted in for what z is, you got this equation. And since this is squared, it can be written like this. But this piece here, this is a matrix. These are all vectors, a vector product. It creates a matrix. And this SP is a matrix. So to extend the two group case, we replace this matrix with two groups with H, which is the between variance or between covariance matrix, and we replace the pooled sample variance with E, which is the within groups variance or covariance. And I'm going to point you back to the video on multivariate one-way analysis of variance for the definition of H and E, but it's essentially the group variance or the between variance divided by the within variance, and we want to maximize this so it creates this maximum distance between the transformed means. Well, it turns out the solution of A is the eigenvector of this matrix product, the inverse of E times H, and this eigenvector corresponds to the largest eigenvalue, lambda 1. And that's it. So our discriminant function is Z1 is equal to A1 transpose times Y. We transform all our data with this transformation, and it creates maximal separation between the group means, or at least the transformed group means. But ultimately, this may not be able to separate the groups, just one transformation. So we may have to create another transformation, and we do that using the second largest eigenvalue and the eigenvector associated with it. Okay, and then we create another transformation. Let's call it ZI, and it's AI transpose times Y, and where AI is the ith eigenvector. And then we can keep doing this as long as we have eigenvectors to make transformations with. Now, how many do you use? Well, it depends. How much of the total variance or variation is described. Well, this is the general or the rule of thumb formula. So, but in general, 2 or 3 discriminant functions is enough to describe the group differences. But you look at the relative importance with this formula. So you take all the eigenvalues, add them up, that's the denominator, and then you look at one at a time the relative importance of that eigenvalue, which means the eigenvector is important. Now this will make more sense when we do an example. So let's just jump into it. The data were collected by Bryce and Barker, that's their last names, from Brigham Young University as part of a preliminary study of a possible link between football helmet design and neck injuries. So 6 head measurements were made on each player. There were 30 subjects in each of 3 groups: high school football players, group 1, college football players, group 2, non-football players in group 3. And the 6 variables were this: the head width, circumference, front to back measurements, eye to top of the head, ear to the top of the head, jaw width. And then it turns out, and we're going to illustrate this in R, but it turns out that the eigenvalues of E inverse times H are these 2 eigenvalues. So lambda 1 is 1.9 and lambda 2 is 0.1159. So if we use this formula for relative importance, look, the first eigenvalue accounts for 94% of the total. So really, one eigenvalue is going to be sufficient in our transformation. And when you see the plot at the end of this, you'll go, oh yeah, that makes sense why we only need one. That's it. So let's look at an R example. So we read the data in from a FTP site. It's called T83 Football. And we need the mass library for the linear discriminant analysis. We print the head of the data and it looks like this. Head just prints the first 6 observations. Then we're going to build from scratch these matrices, the E and the H. We're going to take the eigenvalues, but realistically, you use the built-in function. But I'm just showing you that you do get the same values. So here we calculate the H matrix, and I'm going to skip steps, but as all my programs, I put the R code in the comments so you can go look in that in more detail. But essentially we create this H matrix, and then we create the E matrix, and then we calculate the eigenvectors from it, which we get 2 of them. So this is it. So this first one is the first linear discriminant, and the second one's the second linear discriminant. So that 1, 2, 3, 4, 5, 6. So there's 6. This would be A1, and then you take A1 transpose Y, and that creates a Z values. And then you could create A2 transpose times Y, and that creates that second linear function. Now the eigenvalues, we use the eigen function, and it creates the 2 eigenvalues described in the example. And if we look at the relative importance, you can see that the first eigenvalue, which means the first eigenvector, is clearly the most important, which describes about 94% of the total. And the second eigenvalue describes about 5 or 6% of the total. Okay, so that's how you would calculate it by scratch, but we are not going to do that. We're going to use this LDA function, which is linear discriminant analysis. And then when we're going to store it to fit and print fit, and it prints the group means, and here's the linear discriminant functions. Now it turns out that LD1, and let's see if I can go back to the first one up here. This was the first linear discriminant function that we got by scratch. Couple things you notice. This first component is negative, the rest are positive. When we scroll back down, this will be opposite. This one will be positive, and these are negative. So they're a negative times each other. And so as long as they're a constant multiple times each other, they're the same thing. And they are. And so I forget the exact number. It's minus something that you multiply this, and you end up getting this first linear discriminant. So, but this creates like a new axis. And so just because, one vector points in one direction If you take it times a multiple, it kind of reverses the direction and points in the other way. But it's not essentially, it's the exact same line. Okay, so this is it. And look at the proportion of the trace. The first one has about 94% of the total. Second one's 5 to 6%. Now, what we do, we're going to use the predict function to make these transformations. I think in the first video we did it by scratch, or used we actually multiplied it out. But this predict is you take the fit from the LDA and put in data, and we want all the data, but we don't want the group variables, so we subtract it out, and boom, it takes these linear discriminants times each of those. So now Z contains 2 linear discriminants, and so let's just plot them and see what they look like. And then I create ellipses around the data, and I'm not going to go over that, but this is what it created. So this first, the first component is the first linear discriminant function, the Z1, and this is Z2. And then I put ellipses around the data that roughly describes it. And if you take these and shove them down onto this first linear discriminant, you can tell group 1 is clearly separated from groups 2 and 3, right? When you bring these down, it probably doesn't differentiate that. And then the second one, it only had 5% of the total, so it's really not very useful. And as you can see, if you shove these data to this discriminant, the second, the means, there's so much overlap, it's really not very useful. And so that's what that formula does for the proportion of the total, where you look at the ratio of the lambdas. That's an important component of to know how many linear discriminants you use. Now, earlier I said, sometimes 1 is not enough to make a separation. And if you think about it, that let's say the green and the red are right on top of each other, but separated. And when you bring them down to the first linear discriminant function, it doesn't separate them because they're right on top of each other. But when you shove them to the second one, then it's clearly separated. So sometimes it's like a matrix, they're all in their own little cell. And sometimes you have to have both of them to describe the variance. But this one was not needed. So let's look at the let's look at an analysis of variance. Remember, there's 3 groups on our first discriminant, and it's highly significant. This is really, really close to 0, which says, hey, those treatment means are different between the group, the transformed treatment means, as we would expect. And then you got to go, well, which treatment means or groups are different? And so I do a pairwise t-test with no adjustment method, and you can see the comparison between group 1 and group 2 is highly significant. The comparison between group 1 and group 3 is highly significant, and the comparison between group 2 and 3 are not significant. And that's using the first linear discriminant. Okay, so I'm running a little bit over my target time in these videos, so I'm going to stop here. Hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.